The first question today of Unit 2 Current Electricity. A battery of EMF 10 volt and internal resistance 3 ohm is connected to a resistor. If the current is 0.5 ampere, what is the value of the resistance of the resistor? The second question of the same part. What is the terminal voltage of the battery in closed circuit? Okay, so let's see how you solve this. The solution. Now, you remember, students, the formula for current through a cell. If the current through the cell is I and the EMF is E, the resistance external is R and the internal resistance is small r, then this is the expression for the current, that is the total EMF divided by the total resistance. Capital R is the external resistance and small r is the internal resistance. This could also be written as, you can write R plus R is equals to E divided by I. Now, the EMF of the cell has been given as 10 volts and the current is 0.5. So, if you put these values, so that comes out to be 10 divided by 0.5. That is the total resistance in the circuit, external and internal together. If you solve this, that comes out to be 20. Clear? Let this be your first equation. Now students, from this equation itself, we can write R is equals to 20 minus small r. Now the internal resistance is given to be 3 ohm. So you need to just put the value R equals to 20 minus 3. That comes out to be 17 ohms. Now to find out the terminal voltage, we know the formula to be I multiplied by the external resistance. See, let's draw a diagram. This is the external resistance. You have an internal resistance small r. The EMF is E. If you connect a voltmeter in this particular position, you will be getting the terminal voltage. That means this would provide the terminal voltage. Now, if you wish to find out the voltmeter reading, you see simply, if the current flowing through this is I, then the terminal voltage is the potential drop across the external resistance. So if you wish to find out the terminal voltage, you simply multiply the value of the current, that is 0.5, with the value of the resistance that you have found out, that is 17, and that comes out to be 8.54. So this is your answer. Have a look at it. The next question today. See, at room temperature, that is 27 degrees Celsius, generally it's 27, taken as 27 degrees Celsius. The resistance of a heating element, is 100 ohms. What is the temperature of the element if the resistance is found to be 117 ohms? What is given? Alpha, that is the temperature coefficient of the material of the element, is 1.70 into 10 to the power minus 4 per degree Celsius. Let's see how you solve this. See, we know, students, the formula for the resistance at a particular temperature is given as R2, if it is the final resistance, is equals to R1 multiplied by 1 plus alpha into delta T, where delta T stands for the change in temperature. Okay, from this equation, let's find out the value of delta T. The value of delta T comes out to be R2 minus R1 whole divided by alpha multiplied by R1, right? Where R2 is the final resistance, R1 is the initial resistance, alpha is the temperature coefficient. Now, let's put the values as it is given. Delta T equals to the value of R2 final is 117 minus the value initial is 100 whole divided by 1.70 into 10 to the power minus 4 multiplied by the initial resistance. Then the initial resistance is given as 100. If you solve this, the value comes out to be 1000. Since the temperature coefficient is given in degrees Celsius, this ought to be in Celsius. Now this is not the answer, students. This is the difference in temperature. Now see, the value of initial temperature is given at room temperature 27 degrees Celsius. So if you wish to find out the temperature of the element at 117 ohms, then definitely this difference in temperature, that is delta T, would be equals to T2 minus T1, and that is equals to 1000 degrees Celsius. So from this, the value of T2 would be equals to 1000 plus T1, that is equals to 1000 plus 27. So the final value is 1027 degrees Celsius. So the final temperature at which the resistance is 117 ohms is 1027 degree Celsius. That is the answer. The third question of the day. This is a reasoning question. Say, a high tension supply, very high potential difference, say 6 kV, kilovolt, must have a very large internal resistance. Why? Actually, this is the case in case of very high voltage supplies, or those high voltage sources have very high internal resistance, and it's deliberately done. Why is it done? Why is it deliberately done that the internal resistance is more? The reason is, if somehow accidentally, that means somehow the circuit develops a short circuit, the entire circuit network develops a short circuit. Now, short circuit means if there is a short circuit, then the resistance is less. short circuit, resistance becomes less. If the resistance becomes less, then the current in the circuit reaches very high value. This high value of current might produce very high amount of heating effect, which might damage these very costly and very technically very high end devices, could damage these supplies. So in order to prevent this heating effect and damage, the internal resistances is deliberately made high such that the heating effect is low, and even if there is a short circuit, the heating effect, even if it's there, it might not damage this supply and this very important installations. That is why this internal resistance is made deliberately high to keep current values in case of accidents less. This is the reason why very high potential difference supplies, that is high tension supplies, are always having high internal resistance. Another reasoning question, students. The EMF of the driver cell in the potentiometer experiment should be greater than the EMF of the cell to be determined. Why? Now, let's analyze this. Let us first have this diagram of a potentiometer. Suppose this is your potentiometer with a rheostat here, a milliammeter here, with a battery here. If you wish, you can have a key here. Key. This is the rheostat. Okay, fine. This is the potentiometer wire. Let the wire be AB. And when we use another cell, this is the cell. Suppose we have a galvanometer and a jockey to get a balanced point. Let this be E and let this be E dash. Now the question is, why should this E be always greater than E dash? Interesting, this is the driver cell, or this actually is driving the entire thing. So why should the driver cell have greater EMF than the cell which is to be compared, whose EMF is to be found out? Now see, the thing is, suppose this value of E is less than E dash. If E is less than E dash, then the potential drop across the entire length AB will definitely be less than E dash. That means the potential drop across this entire length AB will be less than E dash. And if that happens, it will not be possible to find a balance point or a point where the potential drop across that section of the wire would be able to balance the EMF of the cell. That means no length will have a potential drop which could balance E dash. Hence, this experiment, the entire idea of this experiment will fail. Therefore, you will never get any balance point and you will never be able to find out the value of E dash or the EMF. Hence, this is not advisable. Hence, it is always advisable to have the driver always greater than the auxiliary one, that is the E dash. This is why always the driver cell should have a EMF which is greater than the one that you are balancing. The next question: on what factors does the potential gradient of the potentiometer wear depends? I hope you remember what potential gradient is. It's an important term. Let's see. Let us draw the diagram of the potentiometer once again. This is the driver cell. This is the rheostat, the milliammeter which is optional. You could have a key, the rheostat RH, and this is the driver cell. The length of the potentiometer wire is AB, and here you have the auxiliary circuit, whatever you wish to find out. Suppose this is E dash. Now, this particular wire AB would be of a certain length L and a cross-sectional area A. Now, if E is the potential drop across AB, then definitely the potential drop across AB would be written as I multiplied by the resistance of the part AB, or the wire of length L. This could be written as, if a constant current flows, which we know is, would be given like rho L by A, where rho stands for the resistivity of the material of the wire, L stands for the length, and A stands for the cross-sectional area. Clear? Now, as we know, students, potential gradient, which is usually represented by a small k, is given by the total potential difference across the length of the wire whole divided by the length. Now, if you divide this by L, that comes out to be I rho by A. This is the potential gradient K. Right? Now, from this expression, it's very evident the factors on which the potential gradient depend. The factors on which the potential gradient depends are: the first one, it is directly proportional to the current flowing through the potentiometer wire, which generally for all experimental purposes is kept to be constant. We do not want the current to change, so it's kept constant, and a small value, because we don't even want the wire to get heated up. So the rheostat is used to keep a small value of current, and which is measured by the milliammeter. K is also directly proportional to the resistivity of the wire. And the third and the last part, K is inversely proportional to the area of cross section. Here the resistivity too is kept to be small to keep the length or to be high, to keep the length to be very small, manageable I would say. And the area of cross section also, as you know, is kept uniform, and it's not very large either. So these are the factors on which the potential gradient of a potentiometer wire depends upon.